Statistical quality control. Statistical quality control refers to the use of statistical methods in the monitoring and maintaining of the quality of products and services. Quality. We can refer quality in different ways. A conceptual understanding is that it is related to one or more desirable characteristics that a product or service should possess. Traditional definition of quality. Quality means fitness for use. So here we have modern definition of quality. Quality is inversely proportional to variability. Definition of quality improvement. Quality improvement is the reduction of variability in processes and products. Statistical process control. Statistical quality control techniques can be broadly divided into two categories. One is statistical process control techniques and another one is acceptance sampling. Statistical process control techniques are widely used in almost any manufacturing process and are very useful in solving real situation problems, achieving process stability, and making continuous improvement in product quality. The most important among these are quality charts. Variation. The law of variation is defined as the difference between an ideal and actual situation. Causes of variation. Chance causes and assignable causes. In any production process, regardless of how well designed and carefully maintained it is, a certain amount of inherent or natural variability will always exist. This natural variability can be thought of as the joint effect of many small essential unavoidable causes. Variability in quality characteristics can also occur from three other sources: improperly adjusted or controlled machines, operator errors, defective raw materials. Such variability is generally large compared to the chance causes. We refer to these sources of variability that are part of the assignable causes of variation. SWOT control chart. It is very simple but powerful graphic method of finding out if a process is in statistical control or not. Control chart is an effective tool in reducing process variability as much as possible. So here it is a block diagram of the control chart. Along x-axis we have the sample number. Along y-axis we plot the quality characteristic that has been measured or computed from the sample. The chart contains a central line that represents the average value of the quality characteristic corresponding to the in control state. Two other horizontal lines dotted called the upper control line and the lower control line are also shown on the chart. These control limits are so chosen that if the process is in control, nearly all of the sample points will fall between them. As long as the points plot within the control limits, the process is assumed to be in control and no action is necessary. However, a point that plots outside of the control limits is interpreted as evidence that the process is out of control and investigation and corrective action are required. These control charts can be measured or countable. There are two types of control charts for variable and control charts for attributes. For measurable, we use the control charts for variables. For countable, we use the control charts for attributes. Control charts for variables. Here we have three different types of control charts for variables: expert chart, R chart and S chart. So here it is the construction of the control chart. The main steps for the construction of the control chart are as follows. First, we have to select the measurable quality characteristic for which the chart has to be constructed. We have discussed how to select the quality characteristic. Then we decide the subgroup or sample size. After deciding the size of the sample and the number of samples, we select sample unit items randomly from the process so that each unit or item has an equal chance of being selected. Next, we measure the quality characteristic decided in step 1 for which selected item in each sample. Errors in measurement may be due to many reasons. These may be due to use of faulty machine, different methods of taking measurements, inept use of instruments by unskilled or inexperienced workforce, etc. Therefore, care should be taken that measurements are made by experts using standard instruments. Then calculate the sample mean for each sample. Set the control limits by using of any one of these charts. Construct the chart. Interpret the results. If all sample points on the plot line on or in between upper and lower control limits, the process is under statistical control. In this situation, only chance causes are present in the process. If one or more points lie outside the control limits, the control chart alarm that the process is not under statistical control. Some assignable causes are present in the process. So this is the tabular values used to construct a control charts. Here one example. The following data were collected from a process manufacturing power supplies. The variable of interest is output voltage and n is equal to 5. Construct X bar and R chart and check whether the process is under control or not. So here we have the 20 samples and each sample has 5 observations that is given in the question. N is equal to 5. The X bar indicate the sample average and R indicate range of the observations. Here already they given directly. These are the formulas we use to construct the X bar chart and R chart. For X bar chart, to constructing the lower control limit is equal to X double bar minus A2 R bar and central line is X bar double bar and UCL is X double bar plus A2 R bar. Here A2 are the tabular values. And for constructing R chart, LCL is equal to D3 R bar, CL is R bar and UCL is D4 R bar. Here D3 and D4 are the tabular values drawn from the table. So with X bar is equal to already given data, we have X bar and R values for 20 samples. So we are calculating X double bar, the formula, the sum of average of all samples. So adding all the observations, sample mean observations divided by number of observations. So here M is 20. So add all the sample averages. We got the 2081 divided by 20. It is equal to the 104.05. After calculating X double bar, then calculate R bar. R bar is also sum of R divided by M. Already the R values are given in the question. Add all the R's, it gives the 79 and the number of observations are 20. Then the R bar is 3.95. Then A2. So substitute, we know the values for the X double bar and R bar values. Substitute these values in the given formulas. Here the 0.577, it is drawn from the table, and here the 0 is also from the table and 2.114 is also from the table. These are the values of D3 and D4. After substituting all those values, we will get the values for the upper control line, central line and lower control limit. Then draw the chart. The title of the chart, first we are going to draw the X bar chart. X-axis, it is a sample number. This Y-axis, it is a X bar values, what are the values given in the question. Then here this yellow line indicate UCL, and this is the gray line, it is a CL central line. The blue line represents it is LCL. Plot all the values, plot all the X bar values in a graph. This indicate the process map of the graph, the orange color line. So when you observe upper control limit, lower control limit, if all the observations are in between these two, the process is under control. So check it, this orange color line are inside of the UCL and LCL, then we conclude that the process is under statistical quality control, since all the points fall within the control limits. Similarly, construct the X bar chart. Construct the R chart. So this is the X-axis, this is the Y-axis. Y-axis we used to range, and X-axis is the sample number. This is the line represents UCL, this is the line represents CL, and LCL is 0, it is on X. Then this blue line is indicate sample observations, the range of the values. Here the sample number 4, you see it is out of control, it crossed the range of the UCL. So we conclude that the sample 4 fall outside of the control limit. Then the statistical process is not in statistical quality control. One more example, construction of a control chart for mean and the range for the following data on the basis of fuses. Samples of 5 being taken every hour. Comment on whether the production seems to be under control, assuming that these are the first data. So here these are the sample observations are collected. So make a table for all the observations, the sample numbers. 12 observations are there. In the 12 observations, we have the samples of size 5 collected. Then the previous example, the question directly they given the X bar values and range values. Here we have the raw data. We have to calculate the X bar value and range. So these are the samples we have from the first sample number. Calculate the average by using of the formula, the sum of observations divided by the number of observations. Then apply the formula for each and every sample number, then we will get the values this way. Then calculate the range. The range is equal to L minus S. The L indicates the largest value and S indicates the smallest value. So in these 5 observations, the largest value is 87 and the smallest value is 42. The difference between this 87 and 42 is 40. 5. So apply the same to each and every sample number. Then after that, in this example, we're going to calculate the standard deviation chart also. For that, have to calculate the sigma, that is standard deviation values for these samples. Then after calculating the x bar values, range and standard deviations, then substitute all those values in that our formulas. For the x bar chart, LCL is equal to x double bar minus A2R bar, and CL is equal to x double bar, UCL is equal to x double bar plus A2R bar. So that, like a previous example, calculate the average of the sample averages. We got it is a 71.6, and the average of the range, it is 59.67. Then identify the tabular value from the statistical tables. The 0.577, it is a tabular value where n is equal to 5. Then after finding the control limits of the x bar and R chart, then calculate the S chart. So this is the formula. LCL is equal to B3 S bar, LCL is S bar, and UCL is B4 S bar. Here B3 and B4 are the tabular values. We observe it is from the tables. And here S bar is the standard deviation, so mean of the standard deviation of the sample observations. So is the formula to calculate the average of the standard deviation. Already in this given chart we calculate the standard deviations. Find that average of all the standard deviation values by using this formula. S bar is equal to summation S divided by M. The value is 21.444. Then substitute all these values in our control limits. Then we will get the values for the control charts. Then construct the control charts. First, x bar chart. Here x-axis indicate the sample number and y-axis indicate it is a sample mean. Then this yellow color line indicated is a UCL, CL and LCL. So check it and plot all the values whatever we have in the table. Plot the x bar values. This is the x bar values. To plot it in a chart. Then the sample fall out of the control. The sample number 10, it is out of control. We conclude that the process is not in statistical quality control. Then for the R chart, the process is under control because all the statistical points fall in the range of LCL and UCL. Next, S chart. So the S chart is also all the points are in statistical control. See, observe all the points are in the control limits of LCL and UCL. Then control chart for attributes. Let us talk about some control charts used for non-measurable quality characteristics. When products are inspected, they are classified into good and defective products. A defective product is one that has one or more defects. The performance of A process is often accessed by the proportion of defective items produced by the process or by counting the number of defects per unit of the product. Control charts used in this situation are known as attribute control charts. Here we discuss the following attribute control charts: P and NP chart for the control of defective products and C chart for the control of number of defectives per unit. P chart. P is the proportion of defective items produced by the process. In quality control terminology, P is referred to as the process average. An estimate of P is given by P bar is equal to total number of defective items in all the samples divided by total number of items inspected. These are the limits of the control charts. See here one example. Everyday sample of 100 refills is taken as a subgroup. The result of 14-day sample collected are given below. Here X denotes the number of defective refills out of 100 inspected each day. So the proportion of P is equal to X divided by N. So these are the proportionate values. The total of X is equal to 84 and the average of P is 0.06. So substitute these values from the given problem. What are the values we know? The K is the number of lots. So 14 lots we used. In that 14 lots, then is the sample size is 100. The control limits LCL is P bar minus 3 into root of P bar into 1 minus P bar divided by N. Substitute all the P bar values in N value in the given formula. Then we get the negative value, but approximately we are taking it is a 0. Then central line it is a 0.06 and upper control limit is the 0.131. Then you observe the values in the chart. The x-axis, how to construct it is a sample number, and in the y-axis it's the proportionate of defective items. So proportion of defective items we have to plot here. Then the yellow color line indicate the UCL, upper control limit, central line and lower control limit. So you observe this blue colored line. The process is under statistical quality control since all the points fall within the control limits. The construct the control limits of P chart for the following data. So here we have the data for the sample size. These are different sample sizes and the number of defective pens we have. For when you observe the 100 samples, the defective pens are 2. When you observe that the sample size is 121, the defective pens are 2. Like that we have the data given in the question. Then we apply the chart, the sample sizes and the number of defective pens. Then this is a proportion of the values. The average A of the P is 0.012612. Substitute all the values in the given control limits. Then observe the process is under control since all the points fall within the control limits. Then NP chart. Sometimes it is necessary to look at the number of defective items rather than the proportion of defective items. In such situations, we use NP charts instead of P charts. So it is also mostly similar to the P chart. P bar is equal to total number of defective items in all the samples, total divided by total number of items inspected. So these are the formulas we use to calculate control limits for the NP chart. LCL is equal to NP bar minus 3 into root of NP bar into 1 minus P bar. CL is the NP bar and UCL is equal to NP bar plus 3 into root of n p bar into 1 minus p bar. Smart bulbs, including, is a famous LED bulb manufacturer. The supervisor drew a randomly constant sample size of 200 bulbs every hour and reported the number of defective bulbs for each lot based on the given data. Prepare the control chart for the number of defectives and determine whether the process is in statistical control. So here data is 20 lots. The size of the sample is 200 from each lot, and these are the number of defectives identified in the sample. Then substitute the values, calculate the p bar value and substitute in the given formulas. Then we will get that control limits of the charts. Then observe the chart. The process is under statistical quality control since all the points fall within the control limits. The C chart, which are used to find the number of defectives per unit. These charts are useful in situations when the performance of a process is assessed by number of defectives per unit. Note that a unit may be a single product or a fixed type of products. The quality characteristic plotted on a C chart is the total number of defects per unit denoted by C. Usually, Poisson distribution is a good approximation for C. So, these are the control limits for the C chart. UCL is equal to C bar plus 3 into root of C bar. CL is equal to C bar. LCL is equal to C bar minus 3 into root of C bar. For example, in a radio manufacturing company, a random sample of 20 radio sets were taken and inspected. The following table gives the number of defects observed in each of the sample units. So here we have the data for the number of defects CI. The total number of defects are 97. The average is C bar is equal to 4.87. We substitute the values in the given formulas. Then we will get the values for the UCL, CL and LCL. Then observe the chart. In the x-axis we take it as example number, and in the y-axis the number of defects we are taking. And we plot all the points here. We observe the 1 point, it is the first one. This looks like it is out of control. So we conclude that the process is not in statistical quality control.